Hello. This is Lecture 3 in the Linguistic Anthropology course, prepared by Language Lab. In this video, we will explore the fundamental mechanisms behind the emergence of language, symbolic thinking, and human consciousness. This discussion will center on the role of the human brain. The lecture is titled, Event X. Before delving into today's topic, let us briefly review the main conclusions from our previous lecture. 1. Symbolic thinking is a prerequisite for the faculty of language. 2. Acquiring symbolic behavior entails significant risks for an animal species. If a species attempts to establish a common symbolic system, it risks extinction before this system becomes fully functional. Neither gradual environmental changes nor disruptive external events alone can adequately explain such a profound cognitive shift. For instance, even if we assume that a sudden space radiation event triggered a mutation in proto-humans, rewiring their brains for symbolic thinking, we must ask, what adaptive advantage did this mutation provide? What external challenge did this rewiring address? We cannot assume that such a mutation alone would have automatically programmed all individuals to use the same symbolic code. At best, it may have given them the capacity to do so, but why would they? What motivation would have driven them to engage in this risky behavior? This brings us back to our fundamental dilemma. No external challenge would have justified engaging in the highly perilous practice of substituting one thing for another, that is, the adaptation of symbolic thought. From these arguments, two key conclusions emerge. 1. The event X must have been sudden and disruptive, requiring an immediate and effective response. This aligns with the rapid emergence of language and culture in human evolution. It also aligns with the fact that a symbolic behavioral code had to become universally shared within a group almost instantly to be functional. 2. If the event X did not originate from an external factor, it must have occurred within the individuals themselves, specifically, in their brains. This sudden neural rewiring must have posed a severe survival threat to both individuals and the group as a whole. However, because all individuals in the group experienced the same cognitive shift, they shared a common perception of the crisis and its implications. Crucially, their similar brain organization would have prompted a unified response, the adoption of symbolic behavior with a shared code. Despite its inherent risks, this symbolic adaptation must have been the only viable solution to the crisis. In essence, the brain sought to resolve its own internal dysfunction, and the cure it devised was symbolic thinking. Let us now commence our investigation with the following premise. If the human brain has undergone significant rewiring to acquire capabilities that other animals lack, then it must possess distinct characteristics that differentiate it from the brains of other species. If we identify core differences in the anatomy and neuronal architecture of the human brain compared to that of other animals, we may infer that these differences underlie and explain our unique cognitive capacities. Furthermore, such evidence may offer insights into the precise nature of the hypothetical event X that facilitated this transformation. Where should we begin? A logical starting point would be to examine the fundamental qualities of the human brain, as highlighted in standard textbooks on brain physiology. One of the most significant features of brain architecture is plasticity. This term refers to the brain's ability to continuously form, grow, strengthen, and also weaken or eliminate neuronal connections in response to experience and environmental demands. The fundamental principle governing this process is that when a neural circuit supports a useful behavior, it becomes frequently activated. Over time, this circuit stabilizes, forming a habitual neuronal pathway that strengthens and solidifies within the brain. A well-established principle in neurology, formulated in 1949 by the eminent neuropsychologist Donald Hebb, encapsulates this phenomenon. Neurons that fire together, wire together. Frequently used neuronal chains begin to draw resources from other circuits, either co-opting them to support a new function or alternatively, causing them to deteriorate and disappear if they come into conflict. This competitive dynamic was further articulated by the prominent neuroscientist Joel Edelman in his theory of neuronal Darwinism. According to this theory, neuronal circuits constantly compete for brain resources, engaging in a process akin to survival of the fittest. The critical mechanism that supports the continuous rewiring of the brain is known in neuroscience as reentrant signaling. Re-entry is a process characterized by the ongoing bidirectional exchange of signals along reciprocal axonal fibers. Simply put, different neuronal circuits communicate through feedback loops, continually verifying, evaluating, modulating, and updating information. This mechanism enables the brain to function as an integrated whole, allowing individual neuronal circuits to identify new opportunities, adapt, and expand at the expense of others to support essential functions. Brain plasticity, therefore, entails a constant reallocation of neural resources to achieve a more efficient and effective cognitive architecture. This flexibility is essential for two primary reasons. First, in the event of brain damage, unaffected areas can assume the functions of impaired regions. This functional reorganization occurs most successfully in early life, as evidenced by cases of individuals with only one hemisphere who nonetheless maintain fully functional cognitive abilities. Second, plasticity is integral to learning. As new skills are acquired and stored in memory, novel neuronal circuits form, and the overall architecture of the brain continuously adjusts to optimize performance and efficiency based on accumulated experiences. This leads us to a crucial question. Does brain plasticity distinguish the human brain from that of other animals? The answer is no. Plasticity, based on the reentrant signaling mechanism, is a fundamental characteristic of all living brains, even in organisms with rudimentary nervous systems. Even small insects exhibit learning capabilities, demonstrating that brain plasticity is not unique to humans. Nevertheless, it is important to keep the concept of plasticity and reentrant signaling in mind, as these features will prove to be significant in our ongoing exploration of what truly sets the human brain apart. Where should we look next for a distinguishing feature of the human brain? Does brain size matter? The size of the brain itself does not appear to be a determining factor in cognitive capabilities. Although brain size in hominins generally increased over the course of evolution, there is no evidence to suggest that a larger brain alone is responsible for the development of symbolic thinking and language. For example, Neanderthals had larger brains than Homo sapiens, yet there is no conclusive evidence that they possessed language or symbolic thought. Similarly, dolphins and elephants have larger brains than humans, but despite their remarkable intelligence, their capacity for symbolic behavior remains limited. As linguist Derek Bickerton observes, some large individuals of the Homo erectus species may have had brains larger than those of some modern humans. However, Homo erectus did not develop language or culture. Furthermore, brain size varies significantly among humans, and scientific research has not established a direct correlation between absolute brain mass and creative intelligence. For instance, the brain of Jonathan Swift weighed approximately 2 kilograms, whereas the brain of the renowned physiologist Ivan Pavlov weighed only 1.5. These findings suggest that creative intelligence and cognitive abilities associated with symbolic thinking are not merely a function of brain size, but rather the result of more complex neural and structural factors. If brain size is not the determining factor, could the internal organization of the brain be responsible for human cognitive uniqueness? One possible approach is to examine differences in the relative sizes of various brain regions in humans compared to other animals. Indeed, in humans, the most evolutionarily recent brain structures are both larger and denser than those found in other mammals. Specifically, humans possess a significantly more massive and densely packed neocortex, the upper layer of the brain, as well as an especially large frontal and prefrontal cortex. These brain regions are responsible for processing higher-order cognitive functions such as reasoning, judgment, personality, and self-control. Could it be that the relative size of these cortical areas, in proportion to the rest of the brain, defines what makes us uniquely human? The answer, once again, appears to be no. For instance, the echidna has a frontal lobe that is proportionally larger relative to its total brain size than that of humans. Yet, no one has observed an echidna landing on the moon. This suggests that cognitive abilities cannot be explained solely by the relative size of specific brain regions, but must be understood in terms of more complex neural structures and functional networks. Perhaps we should investigate further the fact that the human cortex is denser than that of other animals. Could the sheer number of neurons in a particular brain region, densely packed together, make a significant difference? This hypothesis is worth exploring, with one important caveat: the greater number of neurons in the human neocortex does not imply the existence of fundamentally different or inherently superior brain cells. As neurobiologist Jack Panksepp stated, an especially important point to remember is that even though the human brain has much more neocortex than other animals of comparable size, this is achieved by the addition of more columnar modules and their interconnections rather than by increasing the quality, i.e., complexity, of cortical columns. Similarly, neuroendocrinologist Robert Sapolsky confirms that neurons in a human brain are structurally similar to those found in a fruit fly or a worm. The key distinction lies not in the quality of the neurons themselves, but in the quantity of neurons within neuronal systems across different species. This distinction is crucial because through a mechanism that Sapolsky refers to as repulsion and attraction, and which Edelman describes as selection, the brain gains more opportunities to develop complex states that give rise to emergent properties. These emergent properties may contribute to the advanced cognitive abilities observed in humans, not as a result of fundamentally different brain cells, but due to the intricate networks formed by an increased number of neurons and their interconnections. This, then, may be the key. A larger quantity of neurons enabled the formation of more complex connections, creating entirely new configurations of neuronal networks that could support novel cognitive functions, such as symbolic thinking and language. This seems like a plausible hypothesis. However, as one scientist aptly put it, when we do not know what happened, we use the term emergent property. Indeed, thus far, no concrete explanation exists for how the increased number of neurons in the human brain led to these cognitive advancements. It is insufficient to merely state that new patterns of neuronal connectivity gave rise to language and symbolic thought. The crucial question remains, what exactly was this new way in which the increased number of neurons organized itself? To explore this further, we must consider a factor that many scientists regard as a fundamental distinction between humans and other animals: encephalization. Encephalization refers to the size of the brain or neocortex relative to body size, a ratio that is significantly larger in humans than in any other species. In his book, The Symbolic Species, neuroanthropologist Terence Deacon, who describes language as an evolutionary anomaly, suggests that the reorganization of the brain in early humans may have been driven by encephalization, that is, by the growth of brain size relative to body size. In his theory of displacement, Deacon proposes that our ancestors evolved a brain that was disproportionately large compared to their body size. If one were to judge by brain size alone, the human body would be expected to match the size of Gigantopithecus, an extinct 8-foot ape, whose fossils have been found in Asia and Europe. Deacon argues that because the human brain developed within a body that was too small for its relative size, it gained excess capacity and overabundance of cognitive potential. He likens this to a highly powerful computer being tasked with solving only simple equations. Eventually, the brain, having surplus processing power, may have begun to engage with more complex challenges. As a result, the points of contact between different neural networks changed, forming new connections, what Deacon terms displacement. This process of neural reorganization, he suggests, led to the emergence of higher cognitive functions, ultimately paving the way for the development of symbolic thinking and language. Let us pause and consider this carefully. According to Deacon, the human brain continued to grow throughout evolution, exceeding the immediate survival needs of the body. In this scenario, one might imagine the brain metaphorically reasoning, "This is becoming too easy, why not engage in something more complex? Why not develop capacities that could lead to symbolic thinking and language?" However, this raises a critical question: are we suggesting that the brain acquired excess capacity merely for the sake of having excess capacity? Furthermore, what drove the brain to expand to such an extent that its very size became a potential threat to the survival of the species? The consequences of this growth are well documented. Due to the large brain, the human head is disproportionately big, making childbirth significantly more dangerous for both mother and infant. Human babies must be delivered prematurely to pass through the birth canal, rendering them far more vulnerable at birth compared to the offspring of other animals. Additionally, to accommodate this larger brain, females evolved wider hips, which in turn reduced the species' overall physical agility and competitiveness. Given these evolutionary trade-offs, it seems unlikely that the brain expanded merely to acquire an idle capacity for functions that did not yet exist. This is especially true considering that symbolic thinking, if it were an unintended byproduct, would have been an exceptionally risky evolutionary experiment. If the development of symbolic cognition came at such a cost, there must have been a compelling adaptive advantage driving this transformation beyond mere excess neural capacity. Thus, the critical question remains, what specific advantage outweighed these significant costs, making the development of higher cognitive functions not only viable but necessary for human survival? What is particularly interesting about Deacon's theory is that it suggests the brain underwent reorganization without the necessity of any external event. Rather, the brain seemingly acted upon itself. Deacon is not alone in this perspective. Many other scientists propose that the brain's unique characteristics may have driven changes in its internal structure. For example, philosopher David Rosenthal, who studies the nature of human consciousness, offers a similar explanation. Doubtless, adaptive pressures favored high cortical mass, and that may have resulted in creatures with far more cortical resources than needed for everyday functioning. Such excess cortical area might then have come to subserve states that represent other cortical states. Thus, creatures could well have developed the actual higher-order states necessary for their mental states to be conscious, even though their being conscious is not itself especially adaptive. Rosenthal provides a clear explanation for why the brain continued to grow despite the spatial constraints of the cranium. According to his view, this growth was driven by adaptive pressures. These external pressures were linear in nature and did not inherently necessitate the development of symbolic thought. However, they nonetheless stimulated the brain's expansion. Rosenthal aligns with Deacon's view that internal brain dynamics, rather than external stimuli, drove its radical restructuring. He suggests that cortical expansion provided a surplus of cognitive resources, which in turn facilitated higher-order thought functions. However, it is worth considering an alternative perspective. Instead of attributing the emergence of symbolic thought to an excess of cortical capacity, we might propose the opposite, that it was a limitation of space within the cranium that necessitated symbolic thinking. In this view, the internal brain event in question, rather than enabling symbolic cognition through surplus capacity, was actually a response to spatial constraints. The brain, in attempting to adapt to the physical limitations of the cranium while still expanding, may have inadvertently given rise to symbolic thought as a compensatory mechanism. This would suggest that the process of cognitive evolution was driven not by an abundance of neural resources, but by the need to optimize limited space, ultimately leading to the emergence of complex mental functions. Let us examine this position more closely. It is well established that in proto-humans, the brain continued to grow, increasing in mass and density by folding and wrinkling its tissues, much like a sponge being compressed in one's hand. We propose that this inward expansion effectively forced the brain into symbolic thinking. To illustrate, when a sponge is squeezed, it decreases in size but becomes significantly denser. Its internal pores collapse, previously disconnected surfaces come into contact, and new connections emerge. Conversely, in the brain, it was not that empty spaces were simply eliminated, rather, areas that were previously unoccupied became filled with new neurons. As a result, the brain's components, specifically its neuronal chains, were pushed closer together, ultimately leading to new points of contact, intersections, and interactions. This process undoubtedly necessitated a fundamental reorganization of the brain's architecture. Neuronal connections had to be rewired, displaced, and restructured to accommodate the increasingly crowded conditions. Additionally, the brain may have required the introduction of new structural elements to maintain efficiency under these constraints. Initially, it adapted by implementing compensatory mechanisms, building bridges over functional gaps, constructing barriers between competing processes, and rearranging spatial organization to optimize shared resources. However, what the brain did not anticipate was that in integrating what seemed to be purely structural modifications into its design, it was inadvertently setting the stage for a profound transformation, one that would fundamentally alter its cognitive processes and, perhaps, lead to unforeseen consequences. It is now time to formulate our hypothesis and define precisely what event X was. However, before doing so, we must first make a brief digression to introduce an influential concept in biology. This concept was introduced in 1979 by paleontologist Stephen Jay Gould and biologist Richard Lewontin in their seminal work, The Spandrels of San Marco and the Panglossian Paradigm, a critique of the adaptationist program. A spandrel is an architectural feature that arises as an unavoidable structural space between two adjacent arches. An architect may neither design nor consciously account for spandrels, but if adjacent arches are incorporated into a building, spandrels will inevitably form as a byproduct of the design. Gould and Lewontin applied this concept to evolutionary biology to explain the existence of certain morphological traits in living organisms that cannot be directly attributed to evolutionary or adaptive pressures. In other words, some biological features have no apparent functional purpose, rather, they emerge as incidental byproducts of structural adaptations required for other, functionally significant traits. If we apply this concept to the brain, constrained within the limited space of the cranium, we can propose that the brain had to develop a new neuronal architecture to maintain the functionality of its circuits. Metaphorically speaking, neuronal chains became adjacent to one another, similar to the architectural arches described in Gould and Lewontin's theory. As a result, structural elements analogous to spandrels likely emerged to accommodate this new design. These spandrel-like structures would have functioned as neuronal no man's land, forming between densely packed functional circuits that had become so numerous and proximate that they risked interfering with one another. Importantly, these spandrel structures would have been composed of neurons as well, yet, like architectural spandrels, they initially served no distinct functional purpose of their own. However, given that they were connected to adjacent functional neuronal chains, these spandrel structures would have been engaged in neural signaling despite lacking an intrinsic function. As a consequence, they may have acted as reflective elements, passively mirroring the activity of their neighboring circuits. Just as a mirror remains functionally irrelevant unless placed before an object to reflect, a spandrel neuronal structure would, in isolation, hold no inherent functional significance. However, because neuronal chains cannot remain idle, they must integrate into the broader network. These intermediary spandrel structures may have begun to replicate, in their own signaling patterns, the activity of the functional circuits surrounding them. As these spandrel neuronal structures remained connected to functional neuronal chains, they provided feedback in the form of reflections of the chain's own activity. It is important to recall that reentrant signaling, the continuous exchange of information between neuronal circuits, particularly those in close proximity, is a fundamental characteristic of brain function. As brain tissue became increasingly dense, the number of these neuronal mirrors would have grown substantially. Eventually, they became so numerous that they began connecting with one another, forming recurrent loops of communication. This process may have led to the emergence of what could be described as an overall neuronal mirror, a structure capable of reflecting the activity of the entire brain. At this point, the brain suddenly became aware of its own processes. To illustrate, imagine hammering a nail into a wall while simultaneously being aware of yourself performing this action. You could then take this a step further, thinking about the very process of thinking, reflecting on yourself as you contemplate hammering a nail into a wall. This recursive loop could, in theory, continue indefinitely. At this moment, one might be tempted to conclude, aha! This is how consciousness emerged. The brain, having developed the ability to perceive its own activity, would appear to have taken the first step toward self-awareness. However, this was still far from what we recognize today as human consciousness. At this early stage, what occurred in our ancestors was not a refined awareness, but rather a cognitive disruption, an overwhelming and chaotic flood of self-referential processing. Rather than a breakthrough, this may have initially resembled a crisis, a kind of cognitive disarray or madness, as the brain struggled to integrate its newfound recursive awareness. But is there empirical evidence for the existence of mirror-like structures in the brain? Today, research suggests that real neural structures exist that closely resemble the mirror spandrels discussed above. In 1995, a team of Italian researchers led by Giacomo Rizzolatti made a groundbreaking discovery. When a monkey observes a familiar action performed by another monkey, the same groups of neurons fire in its brain as those that activate when the observing monkey performs the action itself. For example, when one monkey watches another peel a banana, the neurons that fire in the observer's brain are the same ones that activate when it peels a banana itself. In essence, the onlooking monkey internally experiences the observed action as if it were performing it. These uniquely responsive neuronal groups were named mirror neurons. Subsequent research suggests that humans also possess mirror neurons and that they play a crucial role in conscious mental states and the construction of the sense of self. Moreover, mirror neurons are believed to underlie theory of mind, the ability to attribute mental states to others, and to facilitate empathic connections. Their existence provides strong evidence that the brain has mechanisms capable of perceiving its own perceptions. This process unfolds as follows. First, an individual observes another person performing a familiar action. This observation triggers a neural representation of the action within a corresponding chain of neurons in the observer's brain. However, instead of prompting a physical response, this neural activation transforms into a mental state, a representation of the neuronal process itself. In other words, the observer experiences the action as if they were performing it, effectively generating an internal image of themselves executing the action as though they were the individual they are watching. This phenomenon strongly parallels the spandrel neuronal structures we propose. Like mirror neurons, these structures would not possess a distinct function of their own but would instead relay information received from sensory input back to the sensory system. When neuronal chains responsible for a specific sensory modality receive this reprocessed information, now originating internally rather than externally, they may misinterpret it as coming from the circuits normally responsible for initiating the observed action. Due to the nature of reentrant loops, this information is subsequently redirected to these circuits, signaling to them the completion of the action as though it had been initiated by them. In the process, an internal mental experience of the action is created. At this point, the observer not only understands what the other individual is doing but also gains an intuitive sense of what the other individual feels while performing the action. In this way, it could even be said that the two individuals momentarily function as a single cognitive entity, sharing an internalized experience of the same event. Let us draw some interim conclusions. As brain tissue became denser, a new neuronal architecture was necessary to accommodate an increasing number of neurons and the intensified interactions between them, all within the spatial constraints of the cranium. This revised architecture required the introduction of new structural elements, some of which likely had a spandrel nature, meaning they emerged as byproducts of structural adaptation rather than possessing an independent adaptive function. These spandrel neuronal structures would have been integrated into the brain's functional network through reentrant signaling, a fundamental mechanism of neural communication. They would have formed closed feedback loops with adjacent functional neuronal chains. Lacking an intrinsic functional role, these spandrel neuronal structures would not have generated their own information. Instead, they would have simply relayed back to the functional neuronal chains the same information they had received from them. In this way, they effectively functioned as mirrors, allowing the functional circuits to perceive their own activity. As the brain became increasingly dense, the number of these spandrel structures grew. Over time, they began exchanging information among themselves, eventually giving rise to a global neuronal mirror, a system capable of continuously reflecting the brain's operations in real time. Before proceeding further, let us conduct another reality check. Is evolution not always wise? Does it not guide the development of species in a way that ensures the best possible adaptation to their environment? If this were the case, evolution should have found an optimal way to accommodate the brain's need for expansion within the spatial constraints of the skull. Natural selection would have favored a brain architecture that was both efficient and beneficial to our species rather than one that posed potential risks. Why then do we argue that the emergence of a neuronal mirror in the brain was a disaster for early humans, potentially even pushing them toward extinction? Was this process not preordained, free of risk, and designed from the outset to lead to consciousness as part of an evolutionary plan? Unfortunately, for those who hold this optimistic view, the reality is quite different. Evolution is not inherently wise. Numerous examples demonstrate that adaptations can lead to unintended consequences and even become detrimental to a species. Geneticists Glenn Peter Sita and Mark Ravinet emphasize this point. Contrary to popular misconceptions of evolution as a driver of linear progress, which results only in the survival of the fittest, our own bodies provide multiple examples of suboptimal organization of organs and systems, best explained by ontogenetic constraints. In other words, evolution operates through trial and error rather than by following a predetermined, intelligent plan. It makes blind bets, some successful, others disastrous. When an adaptation proves problematic, evolution may attempt to compensate by introducing additional modifications. However, in some cases, there is simply no viable solution to an inherently flawed adaptation. Here are some examples of unfortunate, if not catastrophic, evolutionary adaptations in various species. 1. The Irish elk's oversized antlers. The Irish elk had massive antlers spanning up to 12 feet. While they were useful for attracting mates and fighting rivals, they became a liability. The sheer size of these antlers likely made movement through dense forests difficult and required significant energy to grow. As environmental conditions changed, this excessive trait may have contributed to the Irish elk's extinction. 2. The saber-toothed cat's oversized canines. While the massive fangs of Smilodon were great for piercing prey, they were also highly specialized tools that may have been a disadvantage when prey availability changed. If their prey evolved or disappeared, Smilodon may have struggled to adapt due to its reliance on this particular hunting method. 3. The panda's inefficient diet. Giant pandas evolved from carnivorous ancestors, but now rely almost entirely on bamboo, which is low in nutrients. Despite having a digestive system suited for meat, they inefficiently process bamboo and must consume vast amounts daily, making them vulnerable to habitat changes. 4. The ocean sunfish uselessness. The ocean sunfish is one of the least efficient swimmers in the ocean, has little control over its movement, and lays an extreme number of eggs, up to 300 million per spawning event, because most won't survive. Their awkward design makes them highly vulnerable to predators and oceanic changes. A common characteristic in all these cases is that in response to selective pressures, a species adapts effectively in the short term, but faces significant long-term disadvantages, potentially even the risk of extinction. To illustrate, imagine a group of wild horses fleeing from prehistoric hunters. In their panic, they follow what appears to be a logical survival strategy, running as fast as possible along a narrowing path. However, as the path leads to the edge of a precipice, they realize too late that there is no good way to correct their course. Evolution, like these horses, sometimes locks a species into a trajectory that initially seems advantageous but ultimately leads to an inescapable crisis. A similar predicament befell early humans. Their brains had been growing unchecked for an extended period, driven by evolutionary pressures. Yet, this relentless expansion may have led to a precarious situation, one in which the brain's own development created cognitive and structural challenges that threatened the very survival of the species. Just as the size of the antlers in the Irish elk interfered with its effective behavioral patterns and ultimately contributed to its extinction, the unchecked growth of the human brain, within the constraints of the cranium, led to a fundamental shift in its cognitive processes, resulting in the brain's capacity to perceive its own mental states, a development that ultimately disrupted its functionality. It is important to clarify that the argument presented here is a hypothesis. The crucial point is not necessarily whether spandrel structures were the cause of functional impairment, but rather that event X was an internal neurological phenomenon that disrupted the brain's perceptual mechanisms. Hypothetically, space radiation could have induced the formation of mirror networks in the brain through mutation. Any external influence capable of simultaneously generating mirror neuronal structures across an entire population could be a plausible explanation. Nonetheless, the hypothesis that neuronal mirrors arose as a spandrel remains a compelling possibility. We will now examine in greater depth why the described reorganization of the brain was an extremely dangerous development, rather than a deliberate step toward the emergence of consciousness. The presence of a large neuronal mirror in the brain, reflecting its entire operation back to itself, fundamentally contradicts a core principle of perception in living organisms. What is perceived must necessarily be external to the process of perception. When an organism perceives the phenomena of its own cognitive process, this is not a normal condition, but rather a profoundly disorienting and potentially harmful one. A measuring instrument cannot measure itself. It can be said that the nervous system functions as a highly sophisticated measuring instrument, assessing external stimuli and generating responses accordingly. The degree of complexity in these responses varies across species, with more developed nervous systems producing increasingly intricate reflexes. In mammals, the nervous system evolves into an exceptionally complex mechanism for processing stimuli, conditioning reactions based on the integration of multiple streams of information. As neuropsychologist Antonio DiMaggio describes, this process results in the formation of dispositional representations. The concept of dispositional representation refers to stored neural patterns that encode past experiences, bodily states, and learned responses. These representations are not directly activated as images or conscious thoughts, but exist as latent neural structures that can be reactivated when needed to shape perception, decision-making, and behavior. By leveraging a repository of stored dispositional representations, and by constructing new composite dispositional representations to respond to new situations, organisms can interact effectively with reality, assuming appropriate bodily states and producing optimal reactions to environmental stimuli. In mammals, this process is primarily regulated by the limbic system, which governs emotional responses. In more advanced mammals, particularly primates, apes, and humans, the cortex and neocortex play increasingly significant roles in modulating reactions. However, one fundamental principle remains unchanged across all non-human forms of life and their reactions to stimuli: these responses are not conscious. A wolf hunting a rabbit does not think, "I am running after a rabbit," nor does the rabbit fleeing from the wolf consciously think, "I am running away from the wolf." The nervous system's measurement of reality, embodied in dispositional representations and corresponding bodily states, extends external stimuli into these bodily states, merging the perceiver and the perceived into an indivisible continuum of reality. What happens then, when a neuronal mirror interferes with this process? The natural integration of perception and response becomes disrupted. Rather than directly generating an appropriate reaction based on a bodily state formed in response to external stimuli, a brain equipped with neuronal mirrors is constantly compelled to distinguish itself from reality. This phenomenon arises from a recursive loop, an infinite regression of mental images in which the brain continuously reflects its own internal processes, disrupting the direct integration of perception and response. Such a condition is profoundly disorienting for a living organism, as the nervous system becomes overwhelmed by secondary perceptions of an illusory reality that multiplies chaotically within its own cognitive framework. The ability to form a coherent response to external reality deteriorates, as competing perceptions emerge, making it unclear which version of reality should be prioritized. Given this cognitive instability, how could the mind escape from this cycle of confusion and self-referential regression? The most effective solution would be to externalize a superficial copy of the percept formed by the neuronal mirror, treating it as an object outside of the perceiving mind and preventing it from re-entering the internal cognitive process. Once externalized, this percept could then be perceived as an ordinary object within the external environment, allowing the brain to generate an appropriate dispositional representation and restore a coherent interaction with reality. If such a strategy could be achieved, the organism would regain a sense of unity with its surroundings rather than experiencing an alienation from reality. At this point, one might exclaim, "But this is precisely what language does." While this realization may seem obvious to us now, it was far from apparent to early hominins who suddenly found themselves experiencing strange and profoundly unsettling mental states. The discovery of language as a means to resolve the dysfunction caused by neuronal mirrors required highly specific and rare conditions to align. The likelihood of these circumstances occurring was remarkably low. Indeed, genetic evidence suggests that our species once experienced a severe population bottleneck, reducing our numbers to as few as 20,000 to 30,000 individuals, with some estimates suggesting a population as small as 1,500. Many geneticists suggest that the population bottleneck occurred between 70,000 and 50,000 years ago, coinciding with the migration of modern humans out of Africa. This timing also aligns with the hypothesized emergence of language. Our hypothesis frames self-referential processing as initially pathological, with language emerging as a stabilizing adaptation to it. We aim to determine whether this thesis can be validated by empirical evidence. Although direct fossil, genetic, and neuroanatomical evidence for this theory remain somewhat uncharted, multiple lines of research offer indirect support for its key components, highlighting avenues for further exploration. 1. Neural reorganization and language emergence. We have previously discussed brain adaptive plasticity. The brain exhibits the ability to reorganize its language network through functional and structural changes. This reorganization highlights its capacity to adapt its neural architecture, which supports the notion that internal neural events can lead to new cognitive functions. Such adaptability may reflect evolutionary processes wherein internal neural reconfigurations give rise to advanced cognitive capabilities, such as language and symbolic thinking. 2. Mirror neurons and self-referential processing. Additionally, mirror neurons play a significant role in cognitive processing. The default mode network, DMN, a network of brain regions including areas with mirror properties, has been consistently associated with self-referential processing. Activation in the DMN is frequently linked to self-specific processes, suggesting a neural basis for self-awareness and introspection. 3. Language as a cognitive stabilizer. The emergence of language as a tool for structuring and externalizing thought aligns with theories proposing that language serves to organize internal cognitive processes. Research indicates that the brain can undergo rapid reorganization within its language network in response to learning and experience. For instance, overlearning sentences can lead to extensive whole brain reorganization, shifting activity from traditional language areas to sensoromotor regions. This adaptability suggests that language functions as a mechanism for managing and stabilizing complex cognitive processes. 4. Emergentism and language development. Emergentist theories propose that complex cognitive functions, including language, arise from the interaction of simpler neural and cognitive processes over time. This perspective supports the idea that language and symbolic thought emerge as adaptive responses to internal neural dynamics, reinforcing the notion that such cognitive capabilities result not only from external evolutionary pressures but also from internal neural developments. Several prominent scholars have explored the idea that language serves as a mechanism to manage and stabilize complex cognitive functions. 1. Michael Ullman, in his declarative procedural model, Ullman posits that language relies on general memory systems, suggesting that linguistic processes are intertwined with broader cognitive functions. This model implies that language contributes to the stabilization and management of complex cognitive tasks by engaging declarative and procedural memory systems. 2. Elizabeth Bates. Bates' research emphasized the role of language in cognitive development and its interrelation with other cognitive processes. She argued against the notion of language as a modular system, instead proposing that it emerges from general cognitive abilities and social interaction, thereby stabilizing and structuring complex cognitive functions. 3. Viorica Marian. Marian's work on bilingualism and multilingualism examines how managing multiple languages can enhance cognitive control and executive functions. Her research suggests that the use of multiple languages strengthens cognitive mechanisms responsible for managing complex tasks, indicating a stabilizing effect of language on cognition. 4. Lorraine K. Oberle. Oberle has extensively studied the neurolinguistics of bilingualism and the cognitive processes involved in language control. Her research indicates that bilingual individuals develop enhanced cognitive control mechanisms to manage language switching, which in turn stabilizes and supports complex cognitive functions. 5. Albert Costa and Jubin Abutalibi. Language control in bilinguals, the adaptive control hypothesis. This work proposes that the demands of managing multiple languages lead to adaptations in cognitive control processes. The hypothesis suggests that language control mechanisms adapt to the interactional context, thereby stabilizing cognitive functions in bilingual individuals. Additionally, the following scholars' work can be cited as providing partial support for the theory. Merlin Donald argues that external symbolic storage, for example, writing, culture, was necessary for cognitive stability. Philip Lieberman explores how neuroanatomical shifts led to linguistic capacity. Stanislas Dehaene suggests that certain brain structures evolved to repurpose existing neural circuits for new cognitive tasks. All the above scholars and works contribute to the understanding of how language functions, not only as a communication tool, but also as a fundamental mechanism for managing and stabilizing complex cognitive processes, thereby corroborating our hypothesis. We extend this principle by saying that language emerged as a compensatory mechanism to address neurological dysfunction, thereby restoring the perception-reaction continuum at a higher level. How did our ancestors ultimately find the solution to their problem? How did they learn to use language as a remedy for the dysfunction introduced by neuronal mirrors? In the next lecture, we will explore this question in detail. To conclude, let us briefly review the key points discussed today. 1. The emergence of language, consciousness, abstract reasoning, the concept of self, and other qualities considered uniquely human resulted from a disruptive, anomalous event in evolution. 2. This event was not external but internal, occurring within the brain of Homo sapiens. It had to be both sudden and disruptive. 3. The event in question was the formation of mirror neuronal structures in the human brain, driven by increased brain density during encephalization. One possible origin of these structures could be spandrel neuronal elements, which emerged as a byproduct of changes in neuronal design necessitated by the increasing density of brain tissue. 4. The emergence of mirror neuronal structures in the brain was not an adaptive advantage, but rather a pathological development. It initially rendered affected individuals dysfunctional and uncompetitive within their environment, placing the species at risk of extinction. 5. The solution to this crisis came in the form of symbolic thinking and language. Although not optimal and inherently risky, it may have been the only viable means of preserving the species. The parasitic mirror images of brain processes needed to be externalized to maintain an individual's connection with reality, and language provided the most effective mechanism for this purpose. However, arriving at this solution was not straightforward. It required a confluence of highly specific circumstances. This concludes today's lecture. The transcript is available in a separate video on the channel. Thank you for your attention, and we look forward to our next meeting.